The mission of Center for Earthquake Research and Information is to study the causes and consequences of earthquakes. Mainly that entails monitoring earthquakes in the central United States, which the Department of the Interior and the USGS fund us to do. So if you get information for earthquakes in the eastern U.S., a lot of it comes from the Center for Earthquake Research and Information. Outside of that monitoring role, our researchers come from all over the world and they have projects all over the world. So you'll find us in every corner of the globe doing different things to understand the puzzles of how the earth works as a system.
Okay, cool. Are there any other major seismic study centers in the region?
Well, there are a lot of earthquake centers. St. Louis University has one. University of Arkansas, Little Rock, Ole Miss. I think in terms of numbers, Center for Earthquake Research and Information is large, with 50 to 55 people, both working on the seismic monitoring issues as staff members, our research scientists like Dr. Horton looking at specific regional and global issues. But we're well distributed all across the region.
Okay. And I guess moving into the threat posed to Memphis and the downtown area, how real is that threat within this seismic zone?
Well, first of all, we don't know everything about how the New Madrid Seismic Zone works. There are a lot of good research theories based on very good data that reasonable people can come to different conclusions on. What we know is that 3 very large earthquake sequences have occurred here in the last 1,500 years. In terms of building codes, we look at those sequences as one event. So that's 3 earthquakes in 1,500 years. That's a 1 in 500 annual probability. That's within the life of a building. That's about a 10% chance you could have a big earthquake within the life of that building. Okay. For magnitude 6s, the probability would be 3 to 4 times higher. Okay,
perfect. And how many quakes occur in a year on average? I mean, within the area, however small.
In the New Madrid Seismic Zone, there are several seismic sources in the eastern United States. The largest in priority would be the New Madrid Seismic Zone, the East Tennessee Seismic Zone, the Wabash Seismic Zone in southern Illinois and Indiana, and the South Carolina Seismic Zone. We've got a new one now with the Central Arkansas Seismic Zone. We're not sure what that's going to be named, probably the Horton Seismic Zone.
Okay.
So we record 200 earthquakes a year in the New Madrid Seismic Zone, about 80 per year in the East Tennessee Seismic Zone. So our instruments and our people are distributed across that area. Those are the 2 most active areas. However, obviously the recent swarm of earthquakes in central Arkansas makes it the most active source in the eastern United States since October of 2010.
Okay, perfect. Aside from being one of the most active, seismically active parts of the region, or of the nation, I should say, what makes the New Madrid Seismic Zone unique?
Well, let me clarify first. California has thousands of earthquakes every year. It's not like California. So probability of occurrence, the most important thing when we plan for future disasters, is low in the central United States, but the consequences are high because they're really a different kind of quake. If you take the same magnitude event, put one in California, put one here in the central United States, the one in the central United States will be felt over a ridiculously large area in comparison. So the deep geology, the underlying geology in the central United States is composed basically, in general terms, hard, cold rocks that allow earthquake energy to spread out with little impedance, as opposed to California, where the deep rocks, and we're talking 10, 20 miles deep here, are relatively hot and shattered, so energy dissipates quickly.
Okay.
Any earthquake has to lose energy in most cases because the wavefront's getting bigger and bigger all the time. It's expanding geometrically, so it has to lose energy. But the rate at which it loses energy, the attenuation, is based on the structures and materials and heat regimes that wave has to travel through.
Okay, excellent. Now, what is known as the last major quake along the fault? What do we know about that?
Well, I guess it would be what you call major. In 1895, a mid-magnitude 6 earthquake occurred on Halloween night in Charleston, Missouri. That's a about the same size as the Northridge earthquake of 1994 in Southern California, where dozens of lives were lost, lots of damage occurred, $40 billion in insured losses. So that's a fairly big earthquake. And remember that those kinds of quakes in the central United States are much more likely to occur than the big one. Having said that, these big ones are also very important too because they affect such large areas. Compared to California, the planning is different when we look at large earthquakes because there'd be many major cities that could be in competition for resources. That's why it's important to plan for that kind of event now. So the Madrid Seismic Zone is different in many ways. They don't happen here as often. When the big ones occur, they seem to occur in sequences, as has occurred over the last 1,500 years. Earthquakes of the same magnitude compared to California are felt over a very large area. There's a lot of social vulnerability in the region. Perhaps 26% of the kids in our public schools are at or below poverty. The Katrina experience shows us that those kinds of communities where you have a structural vulnerability, in Katrina's case it was geographic, and a social vulnerability overlapping on each other. In Katrina it was poor people living in low-lying areas. If we're going to identify those kind of social vulnerabilities in West Tennessee, then we need to find out where you have a lot of people without resources living in poorly built structures. Those are going to be the pinch points. So our infrastructures, most of it hasn't been built for earthquakes. There are many ways we're different than California, but it's important to note that they don't happen that often here, and but it is prudent to prepare. It's up to governments and engineers to figure out ways to make that cost effective based on the economies and the structures of different scales here.
Right. We've done the probability. Is there an approximation of how soon another mid-magnitude earthquake could be expected? I mean, is there a time frame? I know that you said it's on average of about one every 500 years. So would it make sense to say, you know, within the next 2-3 centuries we can expect that?
Well, you know, we don't understand these earthquakes like we do in California. The probabilities that we give are largely time independent. So there's no end date where earthquake equals 100%. What we know is that these earthquakes have happened over a 1,500-year period of time, which is an incredibly short period of time to build statistics for geological processes, but it's pretty much all we have.
Okay.
So given that, I forgot the question.
Just how soon, you know, an approximation of
You're
how
going to
soon.
edit this, right?
Yeah, oh yeah. Just how soon, you know, an approximation of how soon we could expect.
So we don't know when the next large earthquake is going to happen. We don't know about the geology and the characteristics here to assume what characteristic behavior is. There's a lot of good theories, and there are a lot of theories that people agree more with than other theories. That's the way science works, especially when there's so much uncertainty. The biggest thing is we don't understand the driving force that causes earthquakes in stable continental areas, period. So scientists don't agree on why we have big earthquakes here anyway. We can understand why they occur at the boundaries of the Earth's broken plates, the edges of the Earth's plates, like California. Rates of movement, differential movement from across the fault, plug into the right relationships to tell you how often they should happen in 40, 80 years in California. We don't have that knowledge here. So in general, like California, you have earthquakes very generally. Think of it as a rubber band. You stretch the rubber band until it exceeds the strength of the rock, and the rock breaks, and you have an earthquake, and you start the cycle over. It's very cyclical. Here we have a history of sequences of large earthquakes. Does that mean 3 rubber bands? Does that mean all the energy is released after an earthquake in an area where the faults really have a beginning and an end, as opposed to California, where the faults go all the way around the Pacific Ocean, basically? Okay. We still have a lot of uncertainties here. What we know leads us to believe that it's prudent to prepare, especially recent events. The magnitude 5 earthquake in 1976 that occurred in Martry, Arkansas did damage here in Memphis at a distance of 30, 40 miles. That was very surprising because many of them were critical facilities. Not significant structural damage, cracked slabs, broken plaster. But still, we know a magnitude 6 would release 32 times more energy. Doesn't mean 32 times more damage, but it means a lot more.
Okay.
Having said that, so we said magnitude 6 is 25 to 40% probability in any 50-year time window. But we don't know where that magnitude 6 would occur. Although they'd be much more likely to occur, it's going to mean a lot for Memphis and the University of Memphis if it happens on the southern end versus the northern end, 120 miles away. We'll still feel it, but the damage would be much different. We don't have a probability for where within that the fault system the magnitude 6 would occur. If it's a big earthquake, it won't matter that much.
Okay.